All right, so let's go back to thinking about the sample mean from a simple random sample. What's the expected value of the sample mean for a simple random sample? It's, sorry? We have an answer, but a shy answer. I think yeah. It's the mean of the numbers in the box. It's the population mean, right? If we're using the sample mean as an estimate, so if we're trying to estimate the population mean, and we're doing it using the sample mean, what's the expected value of the estimator? It is the population mean, right? Because that the expected value is the average of the numbers in the box, right? The expected value of the sample mean of a simple random sample or a random sample with replacement is just the mean of the numbers in the box. It's the population mean. So the bias of the sample mean as an estimate of the population mean is 0 because the expected value is the population mean and the parameter is the population mean. Those things just cancel, right? Okay. So if that's the case, what's the mean squared error of the sample mean as an estimate of the population mean? We're talking about a simple random sample. Well, the bias is 0. Bias squared is 0. The standard error of the sample mean as an estimate of the population mean, well, in this case, it doesn't matter. It's just the standard error of the estimator. What is the standard error of the sample mean for a simple random sample? Okay, we've got SD box over root n. And this is a simple random sample, so there's one more thing in that. Yep. So SE of the sample mean for a simple random sample is equal to finite population correction times the SD of the box over root n, where n is the sample size, and f is the square root of n minus n over n minus 1, where n is the population size. Ring a bell? Okay. All right, so the mean squared error of the sample mean as an estimate of the population mean is just the square of its standard error, which is just this thing squared. Okay, because the bias, it's an unbiased estimator. The bias is 0, it's said to be unbiased. This is an unbiased estimator. Okay, and then a special case of this is the sample percentage, right? The sample percentage is a special sample mean. Sample mean if the population only contains 0s and 1s. And in that case, so the SE of the sample percentage for a simple random sample, we're still going to get F. SD of the box now has a simpler form. What's the SD of the box? In terms of the fraction of 1s in the box? Uh-oh. So ring a bell if you have a box, it's a 0, 1 box, has a fraction p of 1s. What's the SD? Not ringing a bell? The SD of the box is square root of p times 1 minus p, where p is the fraction of 1s in the box. Okay. All right. Okay, so this is the special case that the population we're drawing from only contains 0s and 1s. And so p is the fraction of 1s, proportion of 1s. Okay? So if we drew a random sample from a box of numbers, simple random sample, we calculate the sample mean, and we get some particular value, this is the sample mean, what does that tell us about the population mean? Could the population mean be here? Could it be here? Yeah. Could it be here? Yeah. We don't know exactly what the population mean is. But what do we know? We know that typically, if this is the population mean, the sample mean is going to be within about an SE of the population mean. Okay? Sometimes more, sometimes less. But the average distance from the population mean to the sample mean is about an SE, okay? And so if we observed that the sample mean was this, and we knew the standard error of the sample mean, then a reasonable estimate would be that the population mean is the sample mean, give or take, about an SE, plus or minus about an SE. Right? That's kind of our chance variability due to the luck of the draw. Okay? This isn't a quantitative statement yet. It's qualitative. We're going to make it quantitative later. Okay? So the sample mean isn't going to be exactly equal to the population mean, but typically it's off by about one standard error. Now, how do we use that here? In order to know what the standard error is of the estimator, we need to know these things. We need to know F. We need to know the SD of the box. We need to know the sample size. We know the sample size. We're pretending that we know the number of numbers there are in the population, the size of the box, size of the list of numbers in the box. But we don't know the SD of the box. Right? Okay. You remember once upon a time we had some exercise where you, like, if you, oh, maybe that's coming up, actually. You're asked if the SD of the box can have only two values if you have a 0, 1 box and you're told what the variance is. Maybe that's an upcoming problem set. It's all a blur. Okay, so what can we do about the fact that we don't know the SD of the box? Well, if we were talking about a general population of numbers, the SD of the box could be arbitrarily large. Yep. There's no sort of upper bound. We can't really get a bound on the error, right? We could have a box that has all one number in it, in which case the SD of the box is 0. We could have a box that has the numbers minus a million, plus a zillion, you know, whatever, and the SD of that box would be enormous, right? So if we don't know what's in the box, we're not going to know the SD of the box. We need some ways of getting around that to try to figure out what the uncertainty in the sample mean is.